I mentioned that we have something like a Softmax layer at the bottom, right? Now, if you look at the output after all of this, and I'm showing you here the results. Okay. What it will come out with is at the end, it comes out to be a fairly small set of outputs after it's gone through 2 max pooling layers. So you expect, well, actually 3 max pooling layers. So you expect that the output will have shrunk. Okay. So finally, the output comes out to be something like the activation would be about 4 times 4 by 20. And where do you think this 20 is coming from? Is the filter size that we saw over here, right? So this 20 is coming out over here. All right. So, so now the question is, okay, once you've got a 4 by 4 by 20 output, remember I said that CFAR, you need to do a categorization out of how many categories? 10 categories, right? Automobiles, cars, trucks, whatever. There are only 10 categories. But you have an output which is 4 by 4 by 20, okay? It's an activation map which is reasonably large. How do you convert a 4 by 4 by 20 matrix, a 3-dimensional matrix, into one of 10 outputs? And remember, the outputs have to be, what should the outputs look like? So ultimately, when you're looking at the output, what do you want the output to be like? What do you think it should be? What kind of numbers are you looking for? You need to decide between one of 10 categories. So what do you think those numbers should be? Sorry? हाँ लेकिन देखें output में, remember when we did an X and an O? Think about that. What was the output? What is the output? Huh? Percentage, exactly. So it basically said, okay, the probability of hitting an X is this much and probability of hitting an O is this much, okay? If it was properly normalized, then the sum of the probability should be equal to what? Should 1, right? So basically it should say, okay, let's say if it's an X and you input it an X, it should say, okay, well, there's a 90% chance of it being an X and 1 minus 90% chance of being an O. So that means 10%, right? So it should be divided into 10. There should be basically, it should be give you an output which gives you probability of being an automobile, probability of being a car, probability of deer, frog, and so on, right? And whichever is the highest probability, you are naturally going to select that, okay? And let's say the probability, you entered a frog and the output turned out to be a frog, and it said the probability of a frog is 30%, but the other probabilities are less than that, okay? That means you would select that the input was a frog, okay? And how would you calculate the loss? You would say, well, was it a frog or not? Let's say it was a frog. So what would the loss be? Let's say the output for frog was 30%, and the actual case was that it was a frog. What would the loss be? 70. It would be 1 minus 0.3, right? So that's how you would calculate a loss. Ideally, you would want to have an output which says 1. When you enter a frog, it should, and if it is a frog, then it should basically be as close as possible to a 1. Okay, the rest of them should all be close to 0, and there should be 1 at the output. Now the question is, how do we convert a 4 by 4 by 20 matrix into a 1 by 10? So basically, we're looking for 1 se lekar ke 10 outputs, and the sum of these should be equal to 1, right? So maybe if you think this is the highest probability, this should be 0.6 or whatever, and the rest of them should be smaller probabilities, right? So the question is, how do we do that? Any ideas? So let's say you have, I'll give you an example where you have, let's say, 3 numbers. Let's say the first, you not doing on a scale of 1 to 10, but let's say you have got 3 outputs, right? And the first one is a deer, the second one is a truck, and the third one is a plane, right? You're trying to figure out what the outputs are. Now, suppose that the output comes out to be a 1 over here, sorry. Yeah, so suppose that you do get an output and it is not 4 by 4 by 20, but it is actually only 1 by 3. I've made your problem very simple, okay? आपके पास एक 1 by 3 का result आता है, which basically means 3 numbers, okay? And now I want to convert it into probabilities. So what's the simplest way that I can convert it into probabilities? Remember, the sum has to be equal to 1 over here, okay? Total se divide karne, so the total comes out to be 6 over here, and you basically, this is say 1 upon 6, 2 upon 6, and 3 upon 6, right? That seems to be the most simplest way of doing it, okay? Now the problem with this is that you get a number which is 50% over here, okay? And you get a number which is 2/3, so that's you're getting 0.6. You're getting 2 upon 6, 0.33, and this is 1 upon 6, whatever it is, right? Now, this could be a technique, all right, but this is not the technique that is normally used. The technique that is normally used is something called Softmax, which I already showed you. Now, what does the Softmax do? What the Softmax basically tries to do is, instead of, if this number is a little higher than this as compared to this, what it tries to do is weight this more. So in other words, we want to make this, instead of 0.5, we want to make it, let's say 0.7 or something, okay? And we want to make 1 to be smaller than 1/6. We want to make it maybe 1 upon 10, for example, okay? We want to stretch it out so that the likelihood, whichever is the highest number, comes out to be much more probable, okay? ताकि आपकी loss भी कम हो, because ultimately you want to say that this has to be equal to 1, and then you're going to subtract it from a 1, okay? So basically the idea of Softmax is to take the numbers and to be able to stretch it out. जो smaller numbers हैं उनको और छोटा कर दें, और जो बड़े numbers हैं उनको और बड़ा कर दें, okay? Now, another technique that could have been used alternative to Softmax, I haven't told you what Softmax is, but there's something called the sigmoid function, right? Remember what the sigmoid function looks like? Looks something like this. It goes between 0 to 1, okay? The sigmoid function, if you remember, and this goes from plus infinity to minus infinity, all right? So this is x, and this is x. For whatever value of x, what was the equation for sigmoid? Does anybody remember? 1 minus e to the power minus x, okay? So when x was 0, this would, I think this is a plus 1 over here. So when x is equal to 0, that's e to the power 0 is 1. 1 upon 1 becomes half. So that comes out to be 0.5. That's an easy way to remember that. What is it if you forget the sign? Now, this thing has the property that, is it outputting, what is the output going to be? If you select sigmoid, okay? If you use sigmoid as a means to make the to choose the probability, what will this do? Will this output come out to be a number which is between what and what? 0 and 1? Does that sound like a probability? Right? So you could use sigmoid to choose a probability, right? But if you choose a simple sigmoid over here and you say, okay, let's make this sigma of x of I, what is the problem? Does the sum come out to be equal to 1? No, it won't, because you have a 1, it will give you a number, which itself is a probability, but it is not going to sum up to 1, okay? So you could use a sigmoid, and that's a technique for doing it. But what the softmax function does, the problem with the sigmoid is that, and I'll show you what the problem is in a few seconds. But what is actually used is something similar to the sigmoid. It's the equation for sigmoid is that you do e to the power x upon e to the power x upon 1 plus e to the power x, I think. Let me just make sure I forget. These equations are a bit tricky. Okay. So, sorry. It has to sum up to 1, right? So what you do is you do e to the power x of I. All right. You take this to the power, and then you divide by the total sum. Okay. And the total sum is going to be e to the power x to the power x of j, and you sum over all j. Okay. So you take this to the power of e to the power 1. You take this to the power e to the power 2, e to the power 3. And then the number over here is going to be e to the power 1 divided by e to the power 1 plus e to the power 2 plus e to the power 3. Okay. So let's take a look at some of the results, what this gives you. I think I had some examples here somewhere. Let me start some of the examples. Anyway, I've got these written down. So just hang on a second. I'm sure I had it somewhere. जी. Softmax, आप कह रहे हैं कि fair नहीं होगा? Clear नहीं हुआ? Okay, just hold on a second. Let me give you a few examples of Softmax. Okay, so here's an example of Softmax. And if you used different options, what would it give you? So if you chose to do a simple sum, if you did the first one, right? This is 1 upon 6, this is 2 upon 6, and this is 3 upon 6. What do you get? 0.17, 0.33, 0.5, right? Now I'm in this particular case, I'm doing the second example. This is taking the sigmoid value and it's summing over all the sigmoid values. Okay. So you get a slight stretch. You notice that 0.5 comes out to be 0.37. Well, it's actually not very good. It's actually doing the reverse thing. So sigmoid is not working out. But if you use the softmax function, which is the following over here, e to the power x divided by the sum of all of the cases, then notice what happens. The 3 comes out to be a 0.67. So instead of 0.5, it becomes slightly larger. The 2 comes out to be a 0.24, so it becomes slightly smaller than a 0.33. The one which corresponded to a 0.17 in this example, it became even smaller, 0.09. Okay, so it sort of stretched it in the direction that the largest number came out to be very large. Okay, so this is a function which is typically used. And if you look at some other examples, you'll see why it's also useful, because this was the simple sum, this was using a sigmoid, and this was using the softmax. S stands for softmax. Okay. Now notice that if you have, here's an example, -1, 0, 1. Remember, the outputs could also be negative, right? Now, if the outputs are negative, could you use the first function? You couldn't. In this particular example, the sum comes out to be 0. So you're dividing by 0, so that's that's no good, right? And even if it wasn't 0, it would be a -1 over something, which would indicate a negative probability, which is not good. So clearly, this is no good if you have negative numbers. So this also has the advantage that if you look at it, what I've done over here is I've taken the same example of 1, 2, 3, and I've just shifted it by 2. Okay, so the 1 becomes -1, 2 becomes a 0, and 3 becomes a 1. Okay, notice that the results are exactly the same, 0.67, 0.24, 0.09. So in other words, even if you shift the entire thing, the result will more or less be the same, will be exactly the same. Okay, so it's shift invariant. So Softmax has all of these properties. If you notice that if you do the something else, even though this is able to handle negative numbers, this was using the sigmoid, but it's not really doing what you wanted it to do. Okay, and I think the number is also not the same. If you look at 0.18, the number is also changing. So it's not shift invariant. So it doesn't have these nice properties. So anyway, sigmoid is the following function, as I've already said. And this is something which is commonly used to convert the output matrix into one of n probabilities. ठीक है? अच्छा, अब सवाल ये है कि if I go back over here, this particular example, oops. So if I go over here, so the question is कि ये जो है Softmax, this is a 4x4x20, right? So how many parameters do you think this is going to have? So this is converting an input. The input to the Softmax is going to be 4x4x20. Okay. How many weights do you think the output matrix is going to have? So you're simply going to multiply all of them. That makes logical because for every one of those inputs, all right, this is a three-dimensional matrix, which is 4x4x20, 20x20 by 4. You need to have one of 10 outputs. Okay. For each one of these outputs, you're going to have an input. Okay. So what is the result going to be? 4x4x20 by 10 as well, because आपके हर input में एक weight होगा. Okay, so you're going to have times 10 over here as well. Does that make sense? Sorry? Why is it times 10? Can anybody answer that? देखिए 4x4x20 कितने हो गए? This is this particular matrix, right? By 10 क्यों आप कर रहे हैं? क्योंकि output भी size 10 है. So sorry, this is 4x4x20, right? This is, I got this wrong, completely wrong. So this is 4x4x20. Okay, so this is an output which is of size 4x4x20, right? That's this output. Okay. Now, how many for each one of these outputs, you're going to link it, it's going to be fully connected. Okay. So for each one of these output points, you want to connect it to each one of the input points. Okay. And the input is a three-dimensional matrix. So 4x4x20 are the number of points over here, the number of pixels. Okay. These are the number of output points. So for each one of them, there's going to be 4x4x20 by 4x20. Okay. And then there are 10 of these. So that's the number of weights that are going to be associated with the output. The number of classes तो कितनी है? Number of classes 10 है. आपने 10 में से decide करना है. लेकिन weights कितने होंगे, parameters कितने होंगे, वो हम calculate कर रहे हैं. ठीक है? So this over here is calculating the number of parameters. So that's going to be 4x4x20 by 10. Is that it? Are we missing something? कुछ miss कर रहे हैं. Sorry? Bias, right? Bias कितना होगा? Bias normally कितना होता है? Remember we did the example with the toggle thing. उसमें bias कितने थे? हाँ? जितनी layer, जितनी क्या कौन सी जितने फिल्टर्स थे के, राइट? तो अगर आपके पास 2 थे तो आपको याद है दो फिल्टर्स थे, राइट? तो यहाँ पर कितने फिल्टर्स होंगे? यहाँ पर यहाँ पर 10 होंगे, राइट? बिकॉज बेसिकली these are the different filters. This is the equivalent of 10. Remember, K is basically the depth of the output. Okay. So this is going to be okay. So the correct answer is 10, and the correct answer is that okay. So for each one of these outputs, sorry, there is going to be a bias. Okay, I'll have to check this out. But for each one of these outputs, there is a bias. Okay, so as you're calculating this weight, yeah, that makes sense because you're doing a multiplication or all of these for this, and then you're adding a bias. Okay, you're adding a bias for each one of these. So the output, the number of bias points are going to be is going to be 10, same as this. Okay, so that gives you an idea of what softmax is. Okay. And to give you so the alternatives that are discussed are not real alternatives. Those are just to make you understand what softmax is. जी. कौन सी वाली स्लाइड अभी जो चल रही थी, ये वाली? This is multiplied by हाँ बाहर जो categories हैं ये multiply, sorry, हम यहाँ पर multiply by 10 क्यों कर रहे हैं? Because we calculating the number of weights. ठीक है, देखें how do we calculate the number of weights? If I just redraw this, okay, what we basically doing is we taking an output which is something like this. Okay, it's 4 by 4 by 20. Okay, and what we're trying to do is we're trying to say, okay, we have to now based on this, we have to calculate a set of probabilities 1 to 10, because each one of them is going to be an output y1 से लेकर y10 तक. Y1 is basically going to say what is the probability of an automobile. Y2 is going to say what is the probability of a deer, and so on, right? There are 10 categories. So the question is how many weights will there be? So the number of weights that is going to be, so for example, for this particular one input is going to be fully connected. Okay, so the softmax layer is a fully connected layer. What it does is for every input, it connects it to every output. Okay, so it's going to have a weight over here W1 से लेकर के Wn तक weights होंगे. So how many weights are there going to be for this particular output? How many? 4 by 4 by 20, right? So that's the number of weights per output. The total number of outputs is 10. So how many outputs, how many weights are there going to be for all of these? It's going to be 4 by 4 by 20 times 10. Okay, so the last number hai, that is the number of outputs. जी. Okay, so the output layer over here is 4 by 4 by 20. देखें, is there anybody else confused or have I lost anybody else? Okay, let me repeat it one more time. आपके पास एक layer पहले, okay, so you've got 2 layers. You've got one layer over here and you've got one layer over here. This is the output layer and this is the layer before that. This is layer number 6, okay, and this is layer number 7. This is layer number 7, this is layer number 6. ठीक है, अब layer number 6 में आपके पास एक output activation map जो आ रहा है, it's 3-dimensional. ठीक है, अब इससे आपको create करना है an output which is 10, it's just a single vector which is 1 से लेकर के 10 numbers तक. Why is that? Because you want to be able to predict one of 10 classes. That was our original problem. Remember, we said कि CFAR में 10 categories हैं. शुरू हमने यहीं से किया था ना. तो हमारे पास 1 of 10 categories है. We want to be able to, when we input an image, we want to know what is the probability of each one of those outputs, whether it's one of the 10 outputs, right? So layer 7 has to be a 1/7 output, right? उससे पहले जो layer है, that is coming out to be a 3-dimensional output, okay? Because all of these CNNs are producing 3-dimensional outputs, शुरू से आखिर तक. Now the challenge for the last layer from the layer 6 to layer 7 is to be able to convert a 3-dimensional matrix into a 1-dimensional matrix. ठीक है, ये challenge है. और हम किस तरह उसको कर रहे हैं? हम ये कर रहे हैं कि जिस तरह हमने पहले x के साथ कनेक्ट किया था, रिमेंबर जब हमारे पास वो वाला एग्जांपल था, हमने आउटपुट में हमारे पास कोई 8 आउटपुट्स थे जी. अभी टेस्टिंग और ट्रेनिंग की तो हमें बात आई नहीं ना, वहां तक तो हम पहुंचे नहीं है. अभी हम सिंपली ये कह रहे हैं हाँ. सो जो आपके पास y hat होगा, यहाँ पे y hat होगा, लेट्स से कि y hat किस तरह का आपका होगा? Y hat will look like something like this: 0 0 1 0 0. The output will be all zeros except for that particular category which was being predicted. So if the input was, let's say, a deer over here, then y3, let's say, is a deer. Okay, so the y hat will say that it is a deer, it's nothing else. Okay, अब आपकी जो ये जो output आया है, this will give you a set of probabilities, right? It will say that, you know, 0.1, 0.2, 0.3, whatever, and then the correct output will, let's say, be 1 over here. Okay, and it will say, well, it was supposed to be a deer, that but I predicted that the probability is 30%, which is good. It's highest from the rest of it, but it should have been 100%. So the loss is 1 minus 0.3, it's 0.7. ठीक है? So are you getting the big picture? ठीक है ना? So this is how you're calculating the number of parameters, and this is how you are converting from the second last layer into the last layer through a Softmax layer. Okay. Okay. So so now let's take a look at some of the other examples. So there's lots of other CNNs that have been used in the past. So if you look at these, as I said, one of the biggest ones which had the most impact was the one that came out of University of Toronto by Geoffrey Hinton. And that was originally called Supervision, but eventually it was called AlexNet. I don't know why they changed the name. And we'll take a look at it. So this has 7 layers, and we'll take a slightly closer look at this in a minute. Okay. इससे पहले जो थे layers, before this, it was non-neural networks. Okay, so ImageNet was a computation, as I said, which is coming out of the university, and it was coming out of Fifi Lee's lab. And before that, that had been going on, I think, from 2007 and so on. So the first 3 years, the top algorithms were essentially non-neural networks. From 2012 onwards, all of the subsequent solutions, even to date, they're all based on deep neural networks. Okay, and we'll take a look at some of these. This was AlexNet, 7 layers, and then people started going crazy, right? They started saying, well, deeper is better. Okay, so GoogleNet came out with something called the VGG network. It had 19 layers. Okay, you can see that these are all the 19 layers. You can see this is a convolution 64, 64. Then this has 128 filters, and then 256 filters, and then 512 filters. And then a FC means a fully connected layer, which is a 4000 layer. And then in the next layer, so these are the winners of ImageNet. Okay. In 2015, the winner was Microsoft Asia, which had a technique called using residual networks. And we'll talk about this a little bit as well. This had 152 layers. So you can see that people just went crazy, right? From 19 layers, they went all the way up to 152 layers, right? They had a lot of computation power, so they said, let's try it out. And in fact, but when you have a large number of layers, you run into trouble. Okay, as I said, if you add more and more layers, does it always help? It doesn't always help. Okay, what are the problems associated when you have 152 layers? When somebody's trying to do an algorithm, why did GoogleNet not try more than 19 layers, right? Because there's laws, it has diminishing returns. Okay, like you can imagine, everything has, there's law of diminishing returns. You can't just keep on doing something and expect that it will continue to give you positive results. One of the problems with going deeper and deeper is that is something called the vanishing gradient problem. Okay, and let me talk a little bit about the vanishing gradient problem. So this was AlexNet. I'm just throwing this at you. This is how they've showed it. It's a little confusing the way they've showed it, but it says a 224 by 224 image. Okay, and then they take a filter of size 11 by 11, okay, with a stride of 4. Okay, so you can see it's quite different from what we studied. And then you can calculate what W2 is and so on. Again, this is an interesting exercise for you to be able to calculate what W2 is. And if you have, and then what they do is they break it up into separate GPUs. Okay, because all of these are using general purpose CPUs, and so you can't do this on a single GPU. So what they do is they separate it out, and then they have filters, 48 filters over here and 48 filters over here. So just to give you an idea of what AlexNet actually looked like. And if you notice that the top layer is also integrated with the bottom layer, and this is going separately, this is going separately, but there is some mixing as well. So these GPUs are also intercommunicating, okay? And the depth of this is based on, what do you think the depth of this is based on? The depth of this is, remember, based on the previous number of filters, okay? So that's something that you'll see again. So this is just to give you a quick idea of how these networks started to perform. So this is their probability of making a mistake. This is their accuracy. So over here, you can see that the shallow networks up to 2012 had fairly large inaccuracies, okay? 28%, 25%, whereas I think humans had an accuracy of about 5%, okay? And as I said, the reason why humans were inaccurate is because the images are really small and sometimes it's confusing. You can confuse a truck for a car, for example, okay? Notice the drop over here. So this is with deep neural networks. With AlexNet, it went from 25% an error to 16%, okay? Then we see GoogleNet sometime down. GoogleNet went up to 19 layers, all right? It dropped from 16% error rate to about 7%, okay? And then there was another major drop, and this was by going up to 152 layers, and this was using ResNet, okay? And we'll talk a little bit about ResNet as well. And then you see that the improvement is not a lot more after that. ResNet was probably one of the better ones. This also shows you the complexity of the algorithms. Now, this is showing you in 3 dimensions. It's showing you if you look at the vertical scale, so it's again showing you the accuracy, okay? On the horizontal scale, it's showing you the number of operations. And the size of this is also showing you the number of parameters, okay? Because parameters and operations are related to each other. As you notice that as you go, the number of operations, the wider the circle is, and this is 2-dimensional, the wider the surface area is, the greater the number of giga operations per second that it's using, okay? So some of the best algorithms, if you look at the ones which have the highest accuracy, they're not necessarily the ones which are the most the most operationally consuming, or the ones which have the highest parameters, all right? So there's something called inception, okay? And if we get a chance, we'll talk about it, but I'm not talking about it today. This came up some time back after ResNet, and you can see that the accuracy, total accuracy in terms of, it had a higher accuracy as compared to ResNet, slightly higher accuracy. And if you look at ResNet versus Inception, it doesn't actually use a lot more parameters, okay? The number of parameters has not increased. You notice that the size is about the same, and the number of operations is slightly increasing, okay? So this is roughly, the whole of CNN. This is all about image recognition and to be able to see which algorithms are best. And some of these are extremely deep networks, such as this here, 152 layers and so on, okay? The VGGs are very powerful, and Inceptions, these are also very powerful. These are freely available. If you want to use them for your algorithm, you can simply download them and apply them. Most of them are open source code, okay? So now let's see what else we want to talk about today. Okay, so we spoke about the vanishing gradient problem, and I said that if you go deeper, there is a problem. And the problem is basically that you have something called the vanishing gradient problem issue, okay? Now, what do we understand by the vanishing gradient? Remember that when we're applying the gradient descent algorithm, we are looking at the loss as compared to the weight, right? So if you have an input over here, and we're looking at the output, let's say this is the weight over here, this is x1, x2, you have an output over here, y, then we're comparing this to y hat, and we're calculating the loss over here, and we're saying how does the loss change with respect to weight, and then we're going to say that wn plus 1 is equal to wn minus the learning rate multiplied by this. This is how the gradient descent algorithm is working, and this is how the back propagation is working, because it basically calculates the loss with respect to w as you go back. So if you're going backwards, then if you want to calculate the loss over here, dl by d, let's say dA over here, this is dA, sorry, this is WA, this is WB, you're going to have something like, some parameters in the middle, and that's how the back propagation algorithm is going to work, okay? So without going into all of those details. Now, the question is, what is the vanishing gradient problem? The problem here is that as you go deeper into the network, okay, if you have too many layers, and if you use the sigmoid function, okay, so here's the sigmoid function, sigma of x. The sigmoid function, remember when we took dy by df, okay, does anybody remember that? This was f over here, and this was the sum, right? And then y was the sigmoid of f, okay? dy by df kya equation tha if it was a sigmoid? Does anybody remember that? It was sigmoid multiplied by 1 minus sigmoid, okay? Now this is the number between 0 and 1. This is also number by 0, 1. If you plot these two, this is sigma of f going from 0 to 1, okay? If you plot sigma times 1 minus sigma, it looks like this, okay? Why? Because as x becomes very large, then one of these two numbers will become very small, right? So this will become close to 1, so this will become close to 0, and this will be as x goes to, let's say, or f goes to, let's say, becomes very large, then this will become, this parameter over here will become, sigma will become close to 1, 1 minus sigma will become close to 0, and when you multiply this, you get something like a 0, okay? Somewhere in the middle, it's like 0.25, and somewhere over here, it goes to 0, okay? So what you're seeing here is that the problem is that if you have um, if you have f to be too large, okay, with a sigmoid function, the derivative is going to involve, if you're using a sigmoid function, parameters which are going to become very small, okay? So over here, it is non-zero, it's fair, it's reasonable, okay? And you're multiplying this, remember that you're multiplying, one of the terms over here is going to be sigma times 1 minus sigma, right? If this parameter becomes really small, it goes almost 0.00001, let's say. What do you think is going to be the output? What do you think is going to be the impact on delta W? Delta W is basically Wn plus 1 minus Wn is delta W, the amount that you're changing W by, okay? That's going to be basically be equal to the learning rate multiplied by the slope, right? Now what we're saying is that the slope has a term in it, which basically is sigma times 1 minus sigma, which is going to become really small if f is large. Anything which is, let's see, even 5 or 10, okay? And this is quite possible. If you have inputs which are fairly large, then the gradient is going to become really small, okay? So delta W, the incremental input, the incremental change in the weights is going to become extremely small, okay? That's sort of like going through an equation like this. You're trying to get to this particular spot over here. You're starting off over here, but the gradient descent is taking too many small steps. So you're never going to get to the end because it's simply taking too long, because the gradient over here, this is the vanishing gradient, okay? The gradient of sigma, the gradient of sigma of f basically vanishes, all right? So if the gradient of the nonlinear activation vanishes, then you have a problem, and the solution is what? What do you think is the solution? आपके पास एक मसला है, non-linear activation आपने जो चुना है, that is not very good. It has a nice property that it makes numbers between 0 and 1, okay? So there are probabilities. It also is differentiable, that's also nice everywhere, minus infinity to plus infinity, but it has a problem that its gradient vanishes, okay? So we're going to use some other one, and guess which one we're going to use? We're going to use ReLU, okay? Sorry. So ReLU ke saath, remember what ReLU was, right? It simply looked something like this. What do you think the slope of ReLU was? Do you think it has a vanishing gradient problem? So the gradient of this is a straight line. Gradient kya hogi? It's going to be 1, right? So the gradient is 1. So will it have a vanishing gradient problem? No. Its gradient is basically going to look something like this. Okay, for all f, its gradient is going to be exactly equal to 1. Okay, it's got a non-linear part. Yahan pe kya gradient hoga? It's going to go to infinity. So it has a problem that at the point 0, its gradient goes to infinity because it's got a change which is So when you have a 0, let's say you have a value of f, okay? The value of f is negative, then the gradient is going to be 0, no change, okay? Agar if the value of f is going to be positive, then the gradient is going to be 1, okay? So it's very simple, but it is non-linear, and so it solves the problem. And it has a nice advantage that it doesn't require a lot of computation. Sigmoid ke liye, you have to calculate sigma, you have to calculate 1 minus sigma, and that requires computation. And if you have millions of parameters, then you can imagine that it takes a lot of computation. So it has two advantages. It doesn't require a lot of computation, ReLU, okay? And the other advantage is that it avoids the vanishing gradient problem, okay? So this way now we can go deeper. Okay, so now all the deep layers that generally use, they use a ReLU activation function. ठीक है, पहली बात ये हो गई. The other problem that happens is that when you have deep layers, it becomes difficult to train them. Okay, and this is kind of a difficult thing to explain, but basically what the ResNet algorithm, basically it's based on a concept which is called residual networks. Okay, now what do you think we mean by residual? जो आप कहते हैं ना residual, remaining part, right? So it has the concept of a remaining part. So basically, I'm just going to tell you what the algorithm is without going into too much detail. But basically, this is what the algorithm is. And it says that if you have x aa hai, I can draw it horizontally as well. Let's say you have an x, okay? And normally you have something like this, okay? You have an x over here, you have a weight over here, you have a nonlinear activation here, and then you've got combinations over here, and then you've got another. So this is a normal process. It's a normal feed-forward network. इसमें ये कर रहे हैं कि they're doing a shortcut. Okay, so what they're doing is they're taking x and they're saying that this output is not only going to have this particular y. Okay, let's say this is y1 and this is y2. So y2 is not only going to have all of these inputs, but it's also going to have a shortcut link. Okay. I'm not exactly sure if it goes over here. Yeah, it goes over here. Okay. So it basically does a shortcut over this particular layer. Okay. Or it could do a double shortcut. So you could have 3 layers and the input over here jumps over 2 of them. Okay. Or you could have 3 or 4, whatever. All right. But basically the idea is that you take an input and you directly connect it to one of the outputs. Okay. And you do it repeatedly. So if you look at this particular network, if you notice, it's got 152 layers and it's jumping over 2 in every step. Okay, so here's a block. This block has 1 shortcut over here, and then it simply repeats itself. Okay, so it's jumping over these 2, then it's jumping over these 2, and so on. It's got a fairly symmetrical structure. Okay, and they keep on doing this, up to 152 layers, and each one of them is called a layer. So this is layer 1, this is layer 2, this is layer 3. So layer 0 jumps over 1 and 2 and goes directly to 3 and so on. Okay. So the residual network has certain advantages. Basically, one of the advantages, if you think about in a simpler way, is that it is able to create. Let's say you're trying to create the identity output. Suppose that whatever input you have, you want to recreate the input at the output. Okay. Now, if you take it through deep layers, you may never get the original input. Okay. So let's say we have an image of a truck, all right, whatever the truck looks like, and we're trying to create an output which is identical to the input. Okay. If we take it through a lot of layers, and we're not doing a softmax, we're simply doing a multidimensional output layer, which is the same size as the input. You're never going to get the same input. You're never going to get the same input simply because you have so many layers and they're never going to get, be trained so well that you're going to get exactly the input. But imagine if you fed the actual input directly to the output. Loss kya hoga? As soon as it gets the same output, the input directly to the output, the loss is going to immediately come out to be 0. So it's going to immediately learn. Okay. So this is sort of an intuitive algorithm as to why the residual networks works well, because it basically tries to shortcut and it tries to provide a solution. It's like, आपके पास exam है, लेकिन आपको किसी ने exam solutions provide कर दिया, right? So if you have the solutions, you're going to get the right answer, right? But the actual answer is not exactly the solutions. It's looking for a slight variation of that. Okay. So हो सकता है कि I might give you an exam paper and I say, okay, here's one of the homework assignments, and I'm giving you the homework assignment. So you can immediately say, okay, this was homework assignment, so the answer is somewhere close to it. And then you make some modifications and you get it. It would be nice if you had answers like that, right? But that's not how the final exam is going to be. No shortcuts in the final exam. Okay, only there in residual networks. But this has a major advantage. Okay, this has this property. So that's all I'm going to say about shortcuts, about residual networks. So it has several advantages. It basically reduces, the main advantage it has is that it also somehow reduces the vanishing gradient problem. Okay. It also uses ReLU, I believe. Okay. So I'm not going to spend too much time on that. There are whole papers on each one of these networks, and if you're interested, you can actually, as you're going through the project, you might want to refer to these papers. Okay, and I'm sure you'll find it easy to get hold of these papers. Okay. All right. So where are we? We've got another 15 minutes, so let's try to talk about the next topic. So that is about it as far as CNNs are concerned. Now, if you notice in the book that I had given you, they had, what they'd done was all the mathematical stuff was done at the beginning, and then all the the interesting part, the architectures were done later on. Okay, that's generally not my style. I prefer that you get the algorithms, then you apply it. Okay, you get some idea as to what you're trying to do, and then you go back and understand more complexities. Okay, so now I'm going to go back a little bit into the mathematics, some of the math, okay, which is used for optimization purposes. So one of the biggest problems is that, as we saw, that if you have a very deep network, besides complexity, what are some of the other problems that you can have? If you have, let's say, extremely deep network, and you have a simple output, you're just trying to differentiate between X and O. You saw this in the tensor playground as well. What if you have a very deep and over complex network? What's the biggest disadvantage besides, sorry, overfitting? Okay, so you don't want to overfit, because what overfitting, so let's try to understand what overfitting is. Okay, so let's say, okay, and one of the basic technique which avoids overfitting is called regularization. Basically, it says, okay, let's try to make the output a little bit more regular. Okay, now what is overfitting? So if you, let's say, if you look at, you have a bunch of inputs, okay, 1 se lekar ke 5 tak, and these are the outputs, right? And you're trying to fit. So this is the output for Y1, Y2, and so on. And you're trying to make a very simple fit, right? So this is a simple linear regression. If you do a linear fit, it's not going to overfit. It's trying to simply do a very simple fit, okay? But what if you try to do a second order fit over here? Okay, it's going to be slightly better. Okay, you can see that if you look at the previous case, the errors was the bigger, all right? And there was perhaps a little bit of it's perhaps going a little bit upwards, okay? So if I do a second order fit, okay, so I'm trying to fit, and I've done this in Excel. I'm sure that all of you know how to do this. If you trying to fit a second order, which means you're not just trying to fit y is equal to mx plus c. What you're trying to do is y is equal to mx squared plus m1x squared plus m2x plus c, let's say. Okay, you're trying to do a quadratic fit. So because it's a quadratic, there will be a slight slope. The error will be naturally less as compared to a linear fit, probably. Okay. But as you try to do an overfit, so this is an nth order. I think I chose a fourth order polynomial. Yeah, it's a fourth order polynomial. So what you can see now, interestingly, this had 1, 2, 3, 4, and 5. So if you have 5 unknowns and you try to fit a 5 minus 1 fourth order polynomial, then the polynomial is going to be an exact fit. Okay, this is something from maths. And it's going to go through every single point. But guess what? It is obviously an overfit. As you can see, Kay, if you look at this, where is this curve going? Okay, this curve is obviously going really crazy, right? It's not supposed. This is not how you expect the output to be. this is acceptable. Even the linear output is acceptable because it says that, as you're going forward, if you try to predict what the value would be, let's say at 8, you could use this linear fit and you could say it would probably be over here. If you try to use a second order fit and at 7 or 8, you would say it would be over here. But over here, if you try to fit it to an 8, it would probably be something extremely crazy, okay? So that's an overfit, clearly. And here's another example of an overfit, okay? So this is saying this is perhaps a polynomial fit, okay? This is fine. But if you try to go through each and every point, you would get this particular curve, okay? So you can see this is extremely crazy. It just shows that if you have too many parameters, if you try to go too deep, you've got serious problems. It's just going to give you results and the results are not going to be showing up in your test cases, okay? So this was your test data. I only gave it 4 points. But guess what's going to happen if I gave it these 4 points, 1, 2, 3, 4, 5, 6. These were 7 points, right? So the test data, this was the data that it was supposed to be working on, okay? That was 7, the training data, okay? So the training data was 7, but let's say if we tested it on one of these points and we gave it this particular point, what would the prediction be? The prediction would be over here. Would that be anywhere close to the training data, what you expect? Obviously not, okay? Now the question is, what are the solutions to resolving this problem? And there are various solutions, okay? So let's take a look at some of these. The first case is called early stopping, okay? And any idea how early stopping works? So let's say that we have training data, okay? And as you can imagine that over time, as you train it, the loss is going to become smaller and smaller, okay, on the training data, okay? But what you can do is if you have, 100 points of data, what you could do is use a certain portion for training and a certain portion for testing, okay? And this could be randomly done. So you could do a shuffle and 20% of that data could be used for testing. Now, what if you tested it out? Where do you think that the test results would be? Would it be below or above this curve? यहाँ पर आपके पास let's say loss आ रहा है कि say the 20%. Do you think that if you took some data from the training data, which was not used as part of the training data, okay, do you think the loss would be higher or about the same or less? It'd be higher, right? Because it wasn't used as part of the training data. So naturally, you would expect that the loss would be higher over here. So let's say this is the circles over here. So you would expect that losses generally would be higher, right? Now, when you start getting to overfitting, what do you think is going to happen? Let's say this is following this curve, but it's a little bit higher above it, okay? What do you think this curve, the training data curve is going to look like? This is training, sorry, I keep mixing this up. This is the testing data, and this is training, right? So how do you think the training curve is going to look like as you go forward in time? It's going down, but it's above it, right? Is it going to keep on going like this? How do you think it's going to go? It's going to start at some point, is going to, instead of going like this, at some point it's going to start going upwards, okay? And why do you think that's happening? वो यहाँ पर जो है basically यहाँ पर ये overfitting हो रही है, okay? So this is the point that what's going on is that everything was going fine. You got your results over here fine, but all of a sudden now you started to overfit and you're starting, instead of getting this particular curve, you're starting to get this particular curve, or you're starting to get this one, all right? And that's just too fine-tuned to that particular result. And so when you give it data which was not part of the training data, the loss is now going to start increasing, okay? And the loss is going to keep on increasing. So so what you could do if you wanted to stop at an appropriate point, naturally, where would be the right point to stop? How would you actually do this? So let's say I gave you this algorithm, right? How would you actually use this algorithm? Okay. So let's say आपने सबसे पहले यहाँ पर at epoch 1 आपने ट्रेनिंग किया, आपके पास ये लॉस आया, ठीक है? Now what do you do next? Then you do the test loss as well, right? So you do it on this particular training data, all right? Then at the same time, you've got a separate test data, and simultaneously you figure out the test loss, okay? Then what do? You go ahead with gradient descent, all of that, you get the next point. You come over here, you simultaneously do the loss calculation on the test data, okay? You come out over here. You keep on doing this, you keep on doing this, and then what happens? At some point, you notice that this is going upwards. The gap between these two is actually, instead of narrowing, it's actually increasing. And the loss over here for the test data is going upwards. Okay, so what do you do then? You, as the name says, you do stopping. You do early stopping. Instead of keep on training it for longer and longer periods, you say, nahi, bas ho gaya. Now if I'm going to train more, it's going to get into overfitting. Okay, so that's a very simple solution. You can apply this algorithm everywhere, and it is always applied. Okay, so every algorithm that you'll see will have overfitting. Will have early fitting built in. And the question is, where exactly, at what point do you do early stopping? Okay, and we'll look at this in more detail as we go forward. Okay. So this is showing this. This is also called the generalization gap. Okay, the gap between the test data and the training data is generally called the generalization gap. Okay. Now another technique that is used, and this is specific to neural networks and deep neural networks. The concept is called dropout. Okay. Now, what do you think dropout implies? We apply that at IBA as well. Okay. Okay. So let's say you have a bunch of inputs. Okay. So this is your deep neural network. It has a whole bunch of input. This is your input layer. This is input. These are your hidden layers. And then let's say you have your output layers. Okay. So, and all of these are fully connected, let's say. Okay. This is your input, hidden layers, and output. So where do you think dropout is applied? So input layer पर भी apply करेंगे? Okay, not input layer, right? You can't drop the input. We'll apply it on the hidden layers. Okay. So what do you think? What are we going to do? Okay. So what we'll cut off the what? Outliers. Okay. So yeah. So that could be one technique. Is that you? Let's say कि आपके पास एक यहाँ पे value आ रही है. The output value over here, let's say y1 over here is coming out to be very large, okay? 10 to power 3 ho gayi. So you may say, well, that seems too extreme. What do we cancel? Should we drop the entire neuron? Should we drop the output? Should we drop the inputs? What exactly are we dropping? Outliers में क्या हम करेंगे? डेटा पॉइंट से क्या मुराद है? न्यूरॉन या उसकी सिनेप्सेस, इनपुट्स, क्या चीज़ हम लिंक्स को ड्रॉप कर रहे हैं या पूरे न्यूरॉन को ड्रॉप कर रहे हैं? सिनेप्स को ड्रॉप करें. तो आपका कहना है कि हम इस पर्टिकुलर इनपुट को ड्रॉप कर देंगे, ये न्यूरॉन रहेगा, न्यूरॉन भी चला जाएगा. Okay, so that's the correct answer. Is that what you do is basically you drop neurons. Okay, and what that means is that you basically उसके साथ जो inputs हैं वो भी drop हो जाते हैं. So if you're dropping this particular neuron, ये जो दो inputs हैं ये भी ज़ाहिर जो links हैं वो भी disconnect हो जाएंगे. अच्छा, now the question is कि are we going to take a look at the extreme values and drop it, or हम randomly drop करें? Okay, so these are good things to think about. There is no, as I said, these are all architectures that people can worry about. Maybe you come up with an idea and you say, I'm going to use, if let's say most algorithms use a random probability P, they toss a coin and they say, okay, the probability of retention, let's say is 0.5 or 0.8, something like that, right? 0.8 would mean okay, for every neuron, we would toss a coin and we would toss a random number. And we would say, okay, if you're using a P of 0.8, then there is a 20% chance that this guy would drop out, which means that agar aapke paas is particular, not output layer, but let's say is particular hidden layer mein, let's say aapke paas 100 neurons hain, so, and you're using a P of 0.8, how many neurons would be left? 80 would be left, right? 20 of those would be randomly dropped and all the connections would be dropped. So that's the concept of neuron. So one technique is that you do it randomly. The other technique, as somebody suggested over here, is that instead of doing it randomly, we use it for extreme values. Now, honestly, I don't know, in most cases that I've seen random, okay? But ho sakta hai, there might be some architectures which are using extreme values. You might have seen it. Have you? Okay. No, but have you seen that being applied in deep neural networks? Okay. So what we have to see is that that's an interesting concept. कि हो सकता है DNNs में अभी तक हमने वो apply नहीं किया हो, and maybe you want to try this out if somebody else hasn't. So that could be a research topic on its own. Okay. So a dropout is, this is how dropout is done. Now, why do you think a dropout? How is it helping? What's the concept and why is it helping? Ji? Hmm. Hmm. Right. नहीं देखें, थोड़ा सा आपका कॉन्सेप्ट गलत है, क्योंकि हम ये नहीं कह रहे हैं कि हम टोटल न्यूरॉन्स को कम कर रहे हैं. And how are we dropping out? That's an important thing. Are we dropping them out permanently? So Pito, we might as well replace it with a smaller neural network, right? What do you think dropout is saying? Huh? No. So if you look at it, dropout is basically saying, think about it. What we're trying to do is trying to come up with a generalized answer. Okay. Now, ab ho ye raha hai neural network mein, and if you might have seen this in the playground, that some of these neurons start focusing on a particular feature, and they really start, become very focused on that particular feature. And that feature may be, let's say somebody, I'm taking a crazy example that somebody has a mustache which looks like this, all right? It's a crazy looking mustache. But somehow this particular neuron, ये जो बंदा बैठा हुआ है यहाँ पर neuron, it's really focused on that particular mustache style, all right? Now you want to generalize it, and you want this answer to be generalized. So what we're going to do is we're going to say that as we're going through the training process, every once in a while, maybe after every certain batches or every certain epochs, after every 10 epochs, or we could even do it after every epochs, every time we go backwards and do the back propagation, what we're going to do is randomly drop a certain percentage of the neurons. Okay. Now, guess what's going to happen? If we drop this neuron over here, which was overly fitted on a particular type of a feature, now all of these are connected over here. Okay. Now, if this is for some instant of time disconnected, and later on it becomes connected again, so the weights are going to remain the same. लेकिन थोड़ी देर के लिए ये जो weights है हमने इसको हटा दिया. Okay. And then after a few epochs, we bring it back in with the original weights. We're not completely going back to zero. All we're saying is that once in a while, we're going to drop one of the weights, one of the neurons. So what's going to happen is that, let's say this output was very heavily reliant on this particular input, okay? And iska weight jo hai always going to 0, 1, and the rest of them were going to 0, okay? Now all of a sudden this input is gone for one epoch, okay? So what that is going to happen is that the reliance of this output on this particular neuron is for a while going to be gone. It can't rely on that neuron. So it's going to start relying on other neurons. Okay? So it's going to try to generalize the results. So agar ek particular neuron bahut zyada focus ho gaya hai, so by removing it for a little while, you're trying to generalize the answer. Okay? If you think about real world problems, sometimes you might have, all of you are working in companies, okay? So in most good companies, you're forced to go on a vacation, right? For 30 days in a year, they say everybody should go on a vacation, right? This is sort of like a dropout. कि आप एक साल में आपको 30 दिन आपको कहा कि भाई आप गायब हो जाए यहाँ से. Why do you think that's happening? Why do you think that's good for a company? Why do you think good companies force employees? People have watched Big Bang Theory, right? I don't know if anybody is a fan of that. I watched that. Usme Sheldon is one of the great scientists, and he's forced to go on a vacation. His boss, his president of the university, says, "You have to go on a vacation," and he says, "No, I don't want to take a vacation." But his boss says, "No, you have to." Okay, so people force others to go on vacation. Uski wajah ye hai कि देखें, अगर let's say people become too reliant on you, all right? So it's sort of like overfitting, because every time you give the boss an answer, but he's always relying on you, and everybody else becomes, wo sab so rahe hain, aapke baaki colleagues hain, and they're all relying on you. You're the guru in that area, and every time you give an answer, they say, okay, he's, Mr. X is right. Now they're over relying on it. Or ho sakta aap kuch galti kar rahe ho, okay? जब आप एक महीने के लिए vacation पर जाएंगे, other people will actually learn to be backups of you, okay? And then they'll figure out, okay, maybe they found out that you were using an algorithm which is actually totally wrong. You were getting good answers for the test data, but जब आप training पर data जो आप लगाए, तो पता चला कि भाई साहब जो ना ये एक equation इस्तेमाल करे तो which was wrong. So it's always good to have dropouts in the system. That's why people are asked to go on vacations. It builds a more robust system. Okay, so that's the analogy with real world system. So dropout में basically यही हो रहा है. And this is what a dropout does, is you take the input, and this is a standard neural network for a while. Let's say if you have a 50% probability, you drop half of these neural networks. The links are also gone, okay? And then in the next instant, you completely change the pattern as well, okay? And then you keep on training. So basically then you develop more robust weights. Ye jo weights develop ho rahe hain, they become a little bit more robust, okay? And overall, the reliance on the test data becomes less, okay? And the training data, then generally you avoid the overall issue of overtraining, overfitting. So succession planning is sort of like that as well, but it's a little different, because succession planning is basically saying that when that particular person is completely gone, who's going to succeed him, right? Here, हम ये नहीं कह रहे succession planning. Here, I'm saying, let's say I'm the CEO of a company. 5 of you report directly to me, right? Now, there's an over-reliance on one person that, I've become used to कि भाई बाकी 4 जो लोग कहते हैं वो गलत कहते हैं. This particular person who says he always has the right answer, right? So I'm over-reliant on him, and I'm basing all my future predictions based on one particular person's algorithm, okay? Other 4 people have already given up. They're saying कि भाई ये तो top banda hai, iska to answer humse hamesha behtar hota hai, I'm not even going to worth try. So when that particular person goes for a short vacation, which is what is going on over here, other people are going to start building up, okay? And then you're going to come up with a more robust algorithm. That's the analogy. As opposed to succession planning, where you're really planning somebody to succeed you, which is not really what we're saying. We're not saying that any one of these will succeed the others. They're all working together. But they're working together, and they're being more collegial in a sense. Okay. So anyway, so this was the second example. Now we'll talk about more examples of dropout in the next lecture.